So what is subgroup? So subgroup is a subset of a group which which is itself a group. Okay, so that means it is not only a subgroup but also not only a subset, but it has a group structure also. Okay, so any subset which is also a group is called a subgroup of a group G. Okay, so all of you know that that Kleins 4 group, it is a 4-order group. That means it has 4 elements, A, B, C. These are 4 elements. So from these 4 elements, we can consider these 2 elements, E and A. Okay, where the composition is actually defined as the composition defined on B4, the Kleins 4 group. So the composition is same. So under this same composition, this E and A forms a subgroup. So just by using composition table, we can see that this EA, so E composition is E, E composition is A. So like this, A composition is A composition is B. So therefore, so it is very much clear that this EA is the 2-point subset of this Kleins 4 group. This forms a subgroup. Okay. Also, if you consider only the identity element from any group, this identity element alone forms a 1-point subgroup. It is called the trivial subgroup. Also, actually, any group is a subgroup of itself. It is called the improper subgroup. Now, let us study a theorem. So, a subset H of a group G forms a subgroup with respect to the composition if and only if A composition B inverse belongs to H for A comma B belongs to H. So, if you choose A and B from H, in that case, so that A composition B must belongs to H. Okay. Joy, can you hear me? Joy?
Yes, sir.
Okay. Okay. So
Yes,
so
sir.
let us come to the okay. So let us come to the proof. So first, let us consider H as a subgroup of G. Okay. So if you consider H as a subgroup of G, in that case, so H is itself a group. If you consider any 2 elements A and B from H, in that case, that B inverse, since B belongs to H is a group, so B inverse also belongs to this actually H, and since A and B inverse both belongs to H and H is a group, so therefore A composition B inverse must belongs to H. So therefore, A composition B inverse is actually belongs to H. So therefore, A comma B belongs to H implies A composition B inverse belongs to H whenever H is a subgroup of G. Now conversely, now we assume that this condition holds. That means for A comma B belongs to H, A composition B inverse belongs to H. Now we have to prove, conversely, we have to prove that this H is a group. That means H is a subgroup. So since H is a, we have to show that H is a subgroup of G. We have to show that this H is actually, it is a, so that means we have to show that H is a group. Since we have to show H as a group, so therefore this we have to show that four properties of group are satisfied. So therefore, first we consider this actually any element A belongs to H. Let us consider any arbitrary element A from H. So since A belongs to H, we can write A twice. Just A comma A belongs to just actually A H এর মধ্যে আছে, তার মানে হচ্ছে আমরা কি আমরা A টাকে দুবার নিয়ে নিলাম. Let us consider A twice. In that case, due to the given condition, A composition B inverse belongs to H. So we can really say that A composition A inverse also belongs to H. So A composition A inverse belongs to H means this E belongs to H, where E is the identity element of G. So therefore the identity element belongs to H. So the next property. Now let us consider any element A from H. Now we consider these two elements A and E and A. So E is the identity element, A is any arbitrary element of H. In that case, due to the condition, E composition A inverse belongs to H. So therefore, A belongs to H implies A inverse belongs to H. So this is the actually we have proved the third condition of the group first, then fourth condition of the group. Now again, now we prove the first condition of a group, that means the closeness property. So let A comma B belongs to H. In that case, since B belongs to H from the previous result or the proof, so we can say that A comma B belongs to H means A comma B inverse belongs to H. Since A and B inverse both belongs to H, in that case A composition B inverse inverse this belongs to H. Since for any two elements A and B belongs to H, A composition B inverse belongs to H. So A and B inverse belongs to H means A composition B inverse whole inverse belongs to H. That means A composition B belongs to H. So A comma B belongs to H implies A composition B belongs to H. So it is closed under the operation. And since G is actually this composition is associative on G, so therefore it is also associative on H since it is a hereditary property. Hereditary property means মানে আমাদের যেরকম বংশ পরম্পরায় যেটাকে বলে আর কি, মানে আমাদের ধরো বাবা বা আমাদের মা তাদের মধ্যে যে প্রপার্টি গুলো আছে সেই প্রপার্টি গুলো কিছুটা আমাদের মধ্যেও আসে, সেই রকমই associativity of a group is a hereditary property. That means if you consider any actually subset of a group, in that case the composition is still associative on that subset. Okay, so therefore we have proved all the four conditions of a group. So therefore H is a group. Since H is a group, that means H is a subgroup of G. Now let us consider an example. So we show that actually any integer which is a multiple of M, any integer which is a multiple of M, okay, so this collection forms a subgroup of the group Z class. Okay, so we consider this subset of Z. Z means the set of all integers. So let's consider the subset MZ. MZ means the all set of all integers which are multiple of M. Okay, so that means 0 plus minus M plus minus 2M and like this. Now let us consider any two elements A and B from MZ. Okay, in that case A is a multiple of M, MK1, and B is also a multiple of M. That means it is the MK2. Like this can be represented as MK2. So K1 and K2 both are integers. Now since B is MK2, it belongs to Z, and operation of Z is here addition operation. So that means with respect to addition operation, the inverse of an element means the negative of that element. Okay, so if you consider actually the inverse of A in Z, that means it is minus A. Okay, so therefore B is MK2, that means B inverse is equal to minus MK2. Okay, so since this B inverse is minus MK2, so A composition B inverse is nothing but A plus minus B. Minus B means the MK2 minus MK1 minus MK2. MK1 minus MK2 means MK1 minus K2 belongs to this so A composition B inverse, this belongs to actually, but this belongs to this MZ. Since this belongs to MZ, that means this A comma B belongs to MZ means A composition B inverse belongs to MZ. So therefore by the previous theorem, it follows that this MZ is a subgroup of G. Now our next theorem is intersection of any subgroups of a group is again a subgroup. So let us consider two subgroups, H1 and H2. We have to show that their intersection, that is H1 intersection H2, is a subgroup of G. So what we have to show? we have to show first H1 intersection H2 is non-empty, and we have to show that H1 intersection H2 is a subgroup of G. So since H1 is a subgroup of G and H2 is also a subgroup of G, that means identity element of G belongs to both H1 as well as H2. Since the identity element belongs to H1 as well as H2, so identity element belongs to this H1 intersection H2. Since this identity element belongs to this H1 intersection H2, that means this identity element, since identity element belongs to this intersection, so intersection of H1 and H2 is non-empty. So since this intersection is non-empty, so now we can prove that this is a subgroup. So let us consider two elements, A and B belongs to H1 intersection H2. So since A and B are two elements which are in H1 and H2, so in that case, A and B both belong to H1 as well as both belong to H2. So A composition B inverse belongs to H1 and A composition B inverse belongs to H2. Why? Because H1 and H2 both are given. So therefore A composition B inverse belongs to the intersection of H1 and H2. So therefore A and B are taken from H1 intersection H2 and A composition B inverse belongs to H1 intersection H2. That means H1 intersection H2 is a subgroup of G. Now, union of any two subgroups may not be a subgroup. Since union of two subgroups can form a subgroup, but most of the times union of two subgroups may not form a subgroup. Okay, so let us consider two subgroups of Z plus, 2Z plus and 3Z plus. 2Z plus means the collection of all even integers. Okay, and 3Z plus means the collection of all the integers which are multiple of 3. Okay, so let us consider two elements, 2 and 3 from 2Z union 3Z. 2Z and 2Z union 3Z means the collection of all the elements, from 2Z and 3Z. Okay, so that means, so 2 and 3 both belongs to 2Z union 3Z. Now 2Z union 3Z is a subgroup of Z. Okay, so if we can actually, if we have to show 2Z union 3Z subgroup of Z, in that case, it must be closed under the operation, addition operation. Okay. Now, 2 and 3 belongs to 2Z union 3Z, but 2 plus 3, it is 5. It is 5. It is not a multiple of 3 and also not a multiple of 2. Okay. So, therefore, 5 cannot belong to this 2Z union 3Z. Okay. So, it's the contradiction. So therefore, 2Z union 3Z cannot be a subgroup under the addition composition. So discussing on some important subgroups of a group. So first we define center of a group. So what is center? Center is ZG. ZG is the center. Center means X belongs to G, such that this ZG is a collection of all those elements of G, X. So such that this X commutes with each and every element of G. Commutes means X composition G equal to G composition X for every element G, small g belongs to capital G. Okay. So therefore, this collection, we have to show that this collection is a subgroup of G. It is called the center of G. Okay. So now, first we show that this center of G is non-empty. Okay. So actually, E composition G is equal to G, and it is equal to also G composition E, because if we actually compose the identity element with any element on the left hand side or the right hand side, you can get the same element. So therefore, E composition G and G composition E both constitutes G. So therefore, this E identity element, this gives you this actually commutes with each and every element. Okay, so it commutes with each and every element of G. So that means this element E is belongs to actually the center of the group G. Okay. Now we show that it is a group. So let us consider two elements A and B from the Z. So what we have to show? we have to show that A composition B inverse belongs to the center of the group ZG. So therefore, what we have to show? We have to show that A composition B inverse commutes with each and every element of the group. Okay. So now we are starting from A composition B inverse composition G. Now A composition B inverse composition G means what? A composition B inverse composition G by us using the associative property. Now B inverse composition G means G can be written as G inverse whole inverse. So we are taking here G inverse whole inverse in place of G. Now, since it is B inverse composition G inverse whole inverse, it can be written as G inverse composition B whole inverse. Why? Because আমি এটা আগের দিনই বলেছি যে A composition B inverse is nothing but B inverse composition A inverse. Okay. So therefore, A composition B composition G inverse. So this is G inverse composition B whole inverse. Now B belongs to ZG. We have already taken A and B from ZG. So ZG commutes. So any element of ZG commutes with each and every element of G. That means B also commutes with G inverse. So we just actually reverse the order. So G inverse composition B will be B composition G inverse now. Now we are again applying A comp B inverse equal to B inverse composition A inverse. So if we apply this will be G inverse whole inverse composition B inverse. That means G composition B inverse. So A composition G composition B inverse. So now now we can actually rearrange the parentheses by using the associative property again. So A composition G composition B inverse. So now A is again belong to this ZG. So that means what you can say that A also commutes with G. So that means A composition G can be written as G composition A. So this will be G composition A composition B inverse. So this G composition A composition B inverse. So it gives you so therefore it shows you this A composition B inverse commutes with every element of G. That means A composition B inverse belongs to the center of the group. So now let us come to our next theorem, where we have considered the centralizer of an element. So just like the previous result, we can easily prove that a centralizer of an element, of a particular element, forms a subgroup. So we can easily actually prove it. Okay. So there is a result which is on the actually group of matrices. So we skip this portion. For now, we skip this portion. Now, cyclic group. Sujoy, are you here?
Yes, sir.
Okay. Now, cyclic group. Now, we are coming to our next important group, which is cyclic group. So, what is cyclic group? Cyclic group is a group which is generated by a single element. Okay. So, it is a single element generated set. Okay. So, we can generate each and every element with a single element. Okay. So G can be represented as this. Actually, this sign, এই সাইনটা যেটা দেওয়া এখানে arrow type sign, এটা মানে হচ্ছে গিয়ে G is generated by the element A. So each and every element of G can be written as A to the power some n, where n belongs to Z. That means we can give some power to the element A to represent any arbitrary element of this group. Okay. So let us consider an example. Let us consider Z6 plus. So Z, we have actually, আমি আগের দিনে এটাকে নিয়ে আলোচনা করেছি, ক্লাসেও আলোচনা করেছি, the group of residues. The group of residues. So this group of residues is very important group. Okay, so let us consider the Z6 class. Z6 is the collection of 6 classes, so from 0 to 5. And we show that this group is generated by the single element 1. Okay, why? Because actually, if you consider the power of 1, so actually power, here the power means the, actually if we consider, say, what is the power of an element? If you consider a to the power n, a to the power n means nothing but n times composition of a. Okay, so since it is the entire composition of a, and here the for Z6 plus the operation is addition operation. So therefore a to the power n is nothing but n into a. Okay, a to the power n means a composition n times. So that means a plus a n times. That means it will be n into a. So a to the power n is nothing but n into a in case of Z6 plus. So now we can know that actually this group is generated by this single element 1. How? Because 1 into this class 1 is 1, 2 into this class 1 is 2, 3 into this class 1 is 3, like this. So finally 6 into this 1, this will be actually what? This will be 0. So therefore it is easy to see that all these elements from 0 to 5 can be generated by the single element 1. Okay, so if we compose this like 4 times 1, in that case we get 4, like this. So therefore Z6 is generated by 1. We can show that also Z6 is also generated by 5. Excuse me. So Z6 is also generated by 5. So how? Because you can see that 1 into 5, this will be 5. 2 into 5. 2 into 5 means 10. 10 means the residue. So residue means this 4. Okay. If we divide, this is Z6. So if we divide 10 by 6, what is the remainder? Remainder is 4. So therefore 2 into 5 will be 4. Like this 3 into 5 will be 3. And lastly 6 into 5 will be. Okay. So therefore this Z6 plus is generated by this 1 as well as the element 5. Okay. So Z6 plus is a cyclic group which has exactly 2 generators, 1 and. So if any cyclic group is generated by A, so let G is generated by A. In that case, A is called the generator of G. Okay. So let us prove our first theorem. Any cyclic group is abelian. So let us consider a cyclic group. Okay. So let us consider a cyclic group G, which is generated by some single element A. So let us consider 2 actually elements X and Y from G. In that case, this X can be written as a to the power some R. That means some power R is in the power of A. So X is equal to a to the power R. Similarly, Y can be written as a to the power S. So therefore, X composition Y will be a to the power R composition a to the power X. So therefore, this will be a to the power R plus S. Now, a to the power R plus S can be written as a to the power S plus R. R plus S is equal to S plus R. So therefore, this will be a to the power S composition a to the power R. So therefore, Y composition S. So X composition Y is same as Y composition X for arbitrary elements X and Y belongs to. So therefore, G must be abelian. Abelian means commutative. So any pair of elements from G commutes. So therefore, X composition Y is equal to Y composition X. Therefore, this G is abelian. Okay. So okay. Okay. Now, now our next theorem. Next theorem is a finite cyclic group G is generated by this element A if and only order of the group and order of the element is same. So last day we have already discussed on order of an element and order of a group. Order of an element ধরো a to the power 5 হচ্ছে আইডেন্টিটি হয়ে গেল, in that case 5 is the order of a, ঠিক আছে? If we compose a n times to get our identity elements, in that case n is the order of a. So order of an element is nothing but the least positive integer, such that a to the power that positive integer is constitutes identity element. Okay, so this is the definition of order of an element, and order of a group is very easy. It is the number of elements present in the group. Okay, so okay, so first we consider this order of G is finite. Okay, so G is cyclic. First, let us consider G is cyclic. We have to show that order of G is equal to the order of the generating element A. Okay, so let us consider this order of G as n. Okay, we show that the order of the element is also n. So if order of A is not finite, in that case A can constitute infinitely many elements, but G is finite, so it cannot happen. So since it cannot happen, so A must be of finite order. Okay, now so actually, so therefore, so if you consider any finite group and it is generated by some element, in that case that element must be of finite order. Okay, so now now show that this order of A is also n, order of the group. Okay, now if this order, so say this order of the generating element A is m. So since the order of the generating element is m, in that case there are m elements a square up to a to the power m minus 1. We show that these m elements all are distinct elements of G. Why? Because if you consider actually all the power of the element A, if you consider any power in the element of the element A, you can get only these m elements. Okay, not more than that. Okay, so let us prove this. So let t is any integer. Okay, so this t can be represented as MEQ plus R. So when we divide this integer t by m by division algorithm, what you get? T is equal to m into q plus r, where q is the quotient, r is the remainder. So r must lie in between 0 and m. That is 0 and m minus 1. So a to the power t will be a to the power mq plus r. Mq plus r means a to the power mq composition a to the power r. So this will be a to the power m whole to the power q composition a to the power r. Now we have already considered order of A as m. So or a to the power m e. So that means this will be a to the power q composition a to the power r. So therefore a to the power t is nothing but a to the power r. Okay. So r lies in between 0 and m minus 1, and a to the power t is some a to the power r. So therefore, a to the power t nothing but an element from the set E a square up to a to the power m minus 1. So therefore, if you consider any element, you can show that that element belongs to this m elements. So therefore, actually, we can generate only m elements using this element a whenever order of a is m. But we have already taken that order of G is n. So therefore, order of A and order of G must be same, and therefore order of G and order of A both are n. Conversely, order of G and order of A both are n. So we show that G is cyclic. So since order of A is given as n, in that case, these are E a square up to a to the power n minus. These are only n distinct elements which are generated by the element A. So therefore, it is very much clear that G has only n elements and A constitutes these n elements, E, A square up to n to the power n minus 1. So therefore, G must be equal to this set, this collection, E, A square to the power n minus 1. That means any element of G can be generated by some element small a. That means G is generated by this element A, and therefore G is cyclic. Okay. সুজয় শুনতে পাচ্ছ তো?
Yes, sir.
Okay. So therefore, now there is another case which is order of G is infinite. It is very actually easy. This case is very easy. If order of G is infinite, that means G has infinitely many elements. In that case, order of A cannot be finite. If order of A is finite, it can constitute only finite number of elements. Okay, so therefore order of A cannot be finite, and therefore order of A must be infinite. That is order of G and order of A both are same. Both are infinite. Okay. So actually, we have given some examples. Z4 plus is a cyclic group of order 4. So also this Z4 plus is constitutes actually it is actually generated by two elements, actually class 1 and class 3. Okay, so in Z4 there are 4 elements 0, 1, 2, 3, and it is actually generated by 2 elements 1 and 3. Okay, so this is a cyclic group of order 4. There are also some abelian groups. Actually, any cyclic group is abelian, but there are some abelian groups which are not cyclic. So this planes 4 group, which is an abelian group, but it is non-cyclic group. Okay. So okay. So let us consider this our next theorem. So it is an important theorem that every subgroup of cyclic group is cyclic. Okay. So let G be a cyclic group which is generated by some element small a. So let H is a subgroup of G. We have to show that this H is generated, okay, by some element from the group. That means H is also cyclic. So any element of actually G is of the form a to the power some power, a to the power like a to the power n. Okay, so therefore, since H is a subgroup of G, that means a subset of G. That means any element of H is of the form a to the power r. So let us consider or let us choose a to the power m from H, where m is the least positive integer for which a to the power m belongs to H. Okay, so we now show that this H is generated by this element a to the power m. Okay. Now this x belongs to, now let us consider any x belongs to this H. Okay. So we have to show that this x is actually generated by this a to the power m. Okay. Now since x belongs to H and x actually H is a subset of G, in that case x must be of the form a to the power s, where s is an integer. Now by division algorithm we can show that this, if you just that we have already considered an element a to the power m type where m is the least positive integer. So let us divide this s by this positive integer m. So s will be mq plus t. So since s is mq plus t, where t is the remainder, q is the quotient, so 0 less or equal to t less than m. So this inequality holds. So a to the power s must be equal to a to the power mq plus t. Now a to the power s is equal to a to the power mq plus m whole a to the power mq. Mq means a to the power m whole to the power q. Composition a to the power t. Now a to the power m whole to the power q, it can be written as, so a to the power m whole to the power q whole inverse composition a to the power s. Why? Because a to the power s is equal to a to the power m composition a to the power m whole to the power q composition a to the power t. So if you take a to the power m whole to the power q on the left hand side, how can you write it? you can write it as a to the power m whole to the power q whole inverse composition a to the power s. So that means this will be a to the power m composition a to the power m whole to the power minus q composition a to the power s. So therefore, x is some a to the power s and a to the power m belongs to h. In that case, so a to the power m belongs to h, a to the power s belongs to h. So therefore, h is a subgroup. So therefore, a to the power t belongs to h. But it cannot happen. Why? Because if actually a to the power t belongs to h, it can happen only for t equal to 0 because m is the least positive integer. M was taken as the least positive integer. So therefore, t must be 0. Otherwise, this t will be the least positive integer. So therefore, this s will be mq. Since t is 0, s is mq. S is mq means x can be written as a to the power m whole to the power q. So therefore, any element of h can be generated by a to the power m. So therefore, this h is generated by this a to the power m. So since this h is generated by a single element, therefore h is cyclic. Okay. So এখানে আমরা অনেকগুলো এক্সাম্পল দিয়েছি। সো q প্লাস ইজ নট সাইক্লিক, এটা খুব ভালো একটা এক্সাম্পল যে আমরা যদি যে কোনো ধরো কথা বলছি q প্লাস কেন সাইক্লিক নয়। q প্লাস কিন্তু একটা অ্যাবেলিয়ান গ্রুপ, q প্লাস ইজ অ্যান অ্যাবেলিয়ান গ্রুপ, বাট q প্লাস ইজ নট cyclic. Why? Because if q plus is cyclic, then we can generate any element of q by some single element. But now 1/3 belongs to this h. Okay, now 1/3 belongs to q. Now if you consider any element, okay, as a generator of q,